Hello, class. So in this video, we're going to wrap up the new statistics by talking about both effect size and power. So effect size. Um, Many times in psychology, we want to know how big of an effect is it? Not just is there an effect or is there not an effect, like what statistical significance tells us about, like what null hypothesis significance tells us about. We want to know, is there a big difference or is there a small difference? How large of a difference is it? Will this new training program increase my SAT score by 5 points or 100 points? Okay. This information is important as to whether or not you decide to buy a program or something along those lines. So how big of an effect is there? That's what effect size is all about. Okay, so how big is the effect is very important, especially if we're trying to make policy decisions, especially if we're trying to determine if there is, if we want to purchase a particular program. So we don't just care about statistical significance. Is there an effect or is there not an effect? Okay, many times in academia we get so wrapped up in the determination of is there an effect or is there not an effect that we fail to address the practical importance of a situation. Okay, so knowing the effect size of a statistical effect is very important. So you might have heard some things about sex differences, maybe in something like reading comprehension, where females outperform males for a little bit. You might have heard some sex differences in other domains. For the most part, these sex differences in psychology are very, very minuscule. Okay, yes, there is an effect, but for the most part, that effect is itty bitty, teeny tiny. We can see these by these two population distributions right here. Okay, we see females in red here, we see males in blue here. Imagine that this is something like reading comprehension. Is that anything to write home about? I mean, yeah, it's an effect. Yeah, we need to talk about it. But in the grand scheme of things, this effect, this difference is very, very minute. Look at the amount of overlap there is between the two distributions. There's so much overlap, okay? Okay. And this kind of shows us that there's a very, very small effect. The mean difference between these two distributions is very, very small. And we can compare it to something like this. Okay, here we have a massive difference. Notice how wide the mean difference is between these two population distributions. Notice how small the overlap is in this in these two distributions. This might be something like is space studied or mass studied better for long-term retention? Okay, that's a huge effect. Okay, how about the testing effect? Whether or not you test your memory versus an additional period of study, which one of those increases long-term retention the most? Testing. Typically, you'll see effect sizes like this. Here's the experimental group. Here is the control group. Okay, those are very massive differences, and that means that there's a lot of practical importance. You get a lot of bang for your buck studying either via mass or via spaced study or using testing. Okay, so knowing the effect size is very important. Okay, so when we talked about null hypothesis significance testing, we mentioned that if we have enough subjects, any difference will be statistically significant. Okay, we can eventually get that p-value very, very low. We can eventually reject the null hypothesis. With enough subjects, we can find that any effect is statistically significant. But how about if we want a consistent way of viewing studies across the gambit, okay, that use differing sample sizes? So maybe this one study uses 50 subjects, this other study uses 200 subjects. What is a way that we could compare all those studies to see the magnitude of the population mean difference? Okay, that's what effect size is. An effect size is the size of a difference that is unaffected by sample size, unaffected by the number of subjects we have, and allows standardization across studies. Okay, so we can truly tell, we can compare two studies, this one having 50 subjects, this other one having 200, and look at the size of the effect. So they should be consistent, relatively consistent, even if the number of subjects is different. All right, An effect size tells us practical importance. Okay, is there a big increase with this experimental manipulation? Is there a huge difference between maybe the two sexes, maybe some difference between certain particular individuals? Okay, so another way of looking at effect size is effect size tells us how much two population distributions do not overlap. Okay, I said population distribution. I did not say sampling distribution, because sampling distributions, we can get them smaller and smaller and smaller. We can get the sampling distributions to overlap a smaller and smaller amount with the more subjects that we have. Okay, those sampling distributions get skinnier with the number of subjects. But we care about here for effect size how much overlap there is in the population distributions. The more overlap there is, the smaller the effect. The less the overlap, the greater the effect size. Okay, so the less overlap, the bigger the effect size. So less overlap here, we would say that this effect size is pretty large. A lot of overlap here, we would say the effect size is relatively small. Okay, and so here we're trying to answer the question about practical significance. Should you spend money on this program? Should you adopt this studying technique? How large is this prediction of whether this person is going to be a good employee? Should I adopt this new prediction tool or should I not? Okay, versus statistical significance. Just is there an effect or is there not an effect? Okay, effect size, we care a lot about the practical significance. Okay, so when population means are farther apart, the overlap of the distributions is less and the effect size is bigger. So there's two parts of the effect size. One is the mean difference. Okay, we see condition A and condition B. The variance is the same in both of these situations. Okay, the spread of the scores is exactly the same, but the only difference here is in the mean difference. Okay, there is a greater mean difference here in B than there is in A, and so the effect size would be larger for B than it would be for A. There's less overlap here, more overlap here, so a greater effect size here and a smaller effect size right here. All right, so here we have another situation. We've got A and B again, but notice that the population means are exactly the same. Okay, if you look at my slides, I've lined it up such that the population means are equally different from one another in condition A and in condition B. The difference has to do with the variation, the variability. Okay, in A, there's a greater variance. In B, there's a smaller variance. All right, in B, with the smaller variance, we see less overlap, just this amount right here, versus in A, we see a greater amount of overlap. So the effect size is going to be larger for B than it is A. All right, if something naturally varies a whole lot, you need a much greater population mean difference for there to be an equally large effect size. All right, so variance is important here. The smaller the natural amount of variation there is, leads to a population mean difference having a larger effect size. All right, so a wonderful thing about effect sizes is that we can make fair comparisons across various studies using different sample sizes. So I want you to notice here that these are not population means or not population distributions. These here are sampling distributions. All right, so in A, we probably have a larger number of subjects than what we have in B. All right, the standard error of the mean seems to be smaller in A than it is in B because we probably have more subjects, okay, in situation A than situation B. All right, so the first study compared two samples with very large sample sizes. So the curves are very narrow. The sampling distribution is very narrow. The second study, we have two samples with much smaller sample sizes so that each curve is wider. But we want to make a comparison to see if these studies are actually finding the same thing. Because right now, we might reject the null hypothesis for A, and we might retain the null hypothesis for B. And we would think, oh no, we've came to a different conclusion. Which study is right? All right. Well, we want to make a fair comparison to see if these studies are actually finding the same thing. Okay. So we need to control for the number of subjects that these two studies ran. Okay. So the first study has less overlap, but that doesn't mean that it has a bigger effect size than study 2. We just can't compare the effects and the sampling distributions. All right. So what we might do is try to infer what's happening in the population. Okay. So we're looking at population distributions now instead of sampling distributions. And here we find that the effect is pretty much identical. Okay. The effect is pretty much identical. The effect size is the same in study 1 and study 2. All right, the only difference is the number of subjects. So effect size is a good way of comparing studies using different sample sizes. All right. So how do we calculate effect size? Well, there are many different ways to calculate an effect size. It depends on the statistical tests that we're trying to run. It depends on the kind of research that we're doing. All right, so for instance, in correlational research, a correlation coefficient is actually a good measure of effect size. It tells us the strength of the relationship. Okay, the more that correlation is closer to either 1 or -1, that tells us that there is a larger effect. The closer that correlation coefficient is to 0, the weaker the effect. All right, and you've learned that before in other classes. 1 second. All right. So there's multiple kinds of effect sizes, as I mentioned before, and we're going to learn quite a few in this class. But the effect size for any time we have a mean difference is called Cohen's d. All right. Cohen's d is the effect size for when we're comparing two means. And here's the formula for Cohen's d. All right. It is the mean, our sample mean, minus a population mean, all over the population standard deviation. Now, I should mention this is the formula for Cohen's d if we have a one sample z-test. But it's going to look very similar in all of the different cases in which we're comparing two means. So when we have a one sample t-test, when we have an independent samples t-test, and when we have a paired samples t-test, we're going to have a formula that looks very similar to this. There's going to be two differences between means, and there is going to be a standard deviation at the bottom. Now, this formula should look familiar to you. One is it's the exact same thing as the formula for a one sample z-test, except instead of having in the bottom the standard error of the mean, which remember, the standard error of the mean, let me get my drawing utensil out. Okay. Oh, that's awful. All right, standard error of the mean is the population standard deviation over the square root of n. So all we've taken out here is we've taken out the fact that we're taking the standard deviation and dividing it by the square root of n. So we're essentially taking out the sample size. Well, that kind of makes sense, right? If we're trying to make an honest comparison between all of these different studies, regardless of sample size, it makes sense that we're going to take sample size out of the effect size. All right. It also looks very similar to a z-score. These things are not that different from one another. All right. So we have the difference between the two means, the sample mean minus the population mean, all over the population standard deviation. All right. So that's what Cohen's d is. Now, mind you, the effect sizes are going to change as we move on to different statistics. But for when we're comparing two means, this is the effect size that we're going to use, Cohen's d. The way that we kind of interpret this is, let's say Cohen's d is 1. That means that there is one standard deviation unit difference between the two means. Let's say that Cohen's d is 0.5. That means there's a half of a standard deviation unit between the two means. That's how we would kind of interpret Cohen's d. Now, the statistician that came up with this measure of effect size is a guy by the famous statistician by the name of Jacob Cohen. Jacob Cohen's important for a lot of things in statistics. But Some people ask Jacob Cohen, well, how do I know if Cohen's d is a large effect or a medium-sized effect or a small effect? And Jacob Cohen really resisted giving an answer to this. And but people always clamor to, well, I want to know if this is a large effect or a small effect. So he ends up writing some cutoff points. All right. So if we have a Cohen's d of around 0.2, this means that we have a small sized effect. So a Cohen's d of 0.2, this is about 85% overlap in the population distributions. If we have a Cohen's d of 0.5 or around the 0.5 range, that means that we have a medium-sized effect with about 67% overlap between the two population distributions. And finally, if we have a Cohen's d of 0.8 or larger than that, we have a large-sized effect, which has about 53% overlap between the two population distributions. All right, so that is the proposed guidelines, and people have kind of took off with this. So you'll see papers all the time referring to Jacob Cohen's guidelines, but they're very rough guidelines, and it really depends on the discipline that you're in as to whether or not this effect is large or if this effect is small. Okay, it's really contextualized depending on which branch of psychology that you're in. So let me give you a couple of examples of this. In cognitive psychology, we typically deal with pretty big effects. So if I were to have an effect size of Cohen's d of 0.2, it wouldn't be very much to write home about. Okay, I would think that effect was not very large, and I wouldn't be very happy with finding an effect around that size. But if I was in personality psychology and I found a difference of 0.2, that is a very large difference in that domain, because the effect sizes in personality are typically very small because it's very hard to measure personality compared to things in cognitive psychology. In social psychology, the effect sizes are much smaller than how they are in other disciplines. All right. Typically, I don't want to do it typically there, so forget what I said that. But some domains of psychology, there are larger effects than others. So what is a large effect? What is a small effect? It's really contextualized into what branch of psychology that you're in, what kind of research that you're doing. But again, people love to have these cutoffs, and so they rely on them all the time. It's kind of like the cutoff of 0.05 for our alpha level. Okay, Fisher said it, so we're going to go with it till the end of time. Same thing with these effect sizes with Jacob Cohen. But again, how you truly interpret the effect size depends on the discipline that you're in. But again, we would use, like, let's say that we had a Cohen's d of 0.2. We'd say that the population mean differences is about 1/5 of a standard deviation difference between the two population domains. And there, what I'm doing is just converting 0.2 to a fraction. And we refer to them in differences of standard deviation units. That's how we interpret Cohen's d. All right. So effect size, very important. From now on, I want you to calculate Cohen's d and include the effect size in your step 4. All right. So include your Cohen's d in step 4, and we'll have some practice with that. All right. So another application of effect sizes, there's this new statistical technique. I say new, it really was designed in the 1980s and really caught on in the 1990s and really has flourished for the past 20 years, is this statistical technique called a meta-analysis. What a meta-analysis is it's a statistical analysis on multiple research studies. Okay, you take a research study over here, over there, over there, over there, over there, all studying the same thing, and we combine those research studies together using one statistical analysis. All right, and meta-analysis is very, very powerful. Okay, these are very, very good ways of looking at an area in psychology that has been researched a decent amount, okay? Because you can't really do a meta-analysis for a new branch of psychology because there's just not as many studies to combine. But for a branch of psychology, for a research question on which a lot of people have tried to answer, you can do a meta-analysis. And again, very, very important statistical tool. So what are some reasons for why you would want to conduct a meta-analysis? First one is there truly an effect? Maybe some people find the effect, maybe some people don't find the effect. So is there an effect or not? These studies say there is one, these studies say there's not one. So this is what you do. You go and you collect every study that tends to or has tried to attempt that research question. All right. And there's some studies that find the effect, there's some studies that don't find the effect. All right. And then you combine them in the statistical analysis. All right. And you see what the effect size is when you combine all those studies. Now, what you typically will do is you'll weight the studies by how many subjects people had. Okay, how many subjects the research study had. Because the more subjects, probably the greater the degree of validity. Okay, the less error there is in estimating the true effect size. All right, so we weight the studies by how many subjects that they have. We combine them all and we see, is there an effect or is there not an effect? Good examples of this. So in the field of cognitive training, where some people swear that cognitive training improves everything from curing your ADHD to improving your memory to improving your intelligence. Well, there's plenty of studies that say that that might be the case, but typically they're really, really poorly controlled studies. So we combine those with everybody that doesn't find an effect. And guess what happens? If you combine all of them, we see absolutely no effect. All right. So meta-analyses are very important, okay, especially in determining whether or not there is an effect here or whether or not one person found that effect. And we'll see some examples of that here in a bit. Okay, reason number 2 for conducting a meta-analysis. Well, we can look at what moderators influence the magnitude of the effect. Maybe we can look at something like the age of the subjects. Maybe some studies find the effect because they use older adults, and these other studies don't find the effect because they have younger adults. Now, that's not something that you could look at, maybe doing one individual study, but if you've got a meta-analysis and you see these 6 studies use younger adults and these 5 studies use older adults, then you can make a comparison between the 2 of them. All right, so maybe we can look at aspects of the sample. Maybe we can look at aspects of the independent variable. Maybe we can look at how we measured the dependent variable. And we can see under what circumstances we get a large effect and what circumstances we don't get a large effect. So this is a good way, and it might point to some new research questions in a particular research domain. So what are things that influence the size of the effect? 3, and this is a very important one, is there publication bias in reporting the effect? All right, so we've talked about the file drawer problem in a previous lecture. So there might be the case that only research that finds the effect gets published. So you can do this nifty thing with meta-analysis to see if there is publication bias that's preventing some studies from being published. And we'll talk about that here in a second. So meta-analyses are based on the importance of replication, right? Every study that we conduct is probabilistic. Remember, we have if the null hypothesis is true, we have a 5% chance of rejecting the null hypothesis, which is bad. But being the good statisticians, being the good researchers that we are, we try to replicate our findings again and again and again. If it's something that's true, it should hold not just this one instances, but multiple instances. Okay, so we try to see if previous research findings that say that there is effect, they might be due to some kind of statistical error. All right, so with the meta-analysis, we get a couple of cool graphs that come out of it. One that I want you to know is a forest plot. Now, here for the forest plot, on our x-axis here, we have our measure of effect size. Okay, and here this forest plot is an odds ratio. That's the effect size, but just don't worry about odds ratio right now. Just assume that this is a bigger effect. This means that there's a smaller effect. Okay. And on this forest plot, we have every single study that's in the meta-analysis. Okay. Every study that's in the meta-analysis. And we can see which study it is over here. Now, the size of this square indicates the sample size that the researchers used. So here they had a lot of subjects. Here they had a little fewer. Here we had even fewer. And here probably the same amount as that third study. What we see in this line is the confidence interval. Okay, it's the confidence interval for how large that effect size actually is. All right. Now, what we do is we combine all of these studies. Okay, we combine all of these studies, and we get this diamond shape down here. This diamond shape represents a 95% confidence interval when we smash all the subjects together. So the true effect is probably somewhere around here. If this diamond crosses this bar in the middle, okay, then there is no statistical difference. The conclusion that we have to make is that when we combine all the studies, there's actually no difference between the population means. All right, if we see that this diamond doesn't cross this line right here, that means that there is truly an effect when we look at all of the different studies. All right, if it's over here, the effect is one way. If the diamond's over here, the effect is another way. Okay, is this condition greater than that one, or is this condition greater than the other one? Okay, that's what the side that the diamond appears on. All right, so that's a forest plot, and hopefully you should be able to interpret that if I were to give you a forest plot, or if you were to read it in a paper. Another very, very useful graph that we get from a meta-analysis is a funnel plot. What a funnel plot does is it presents the effect size and the sample size of the study. All right, and each of these dots represents a single study. All right, so each of these dots represents a singular study. Now, here we have the size of the effect on the x-axis. Okay, is mean 1, is this condition greater than the second condition, or is the second condition greater than the first condition? Okay, that's how we interpret what side of this funnel or this triangle we're on. All right, so how big is the effect? We look and see how far it is away from this middle bar here. Now, on the y-axis, we have the precision of the study, how accurate the study is. Okay, so if we have a lot of subjects, we're going to move up on the graph. If we have fewer subjects, we're going to be down on the graph. Now, this triangle here is a prediction of where these studies should fall. If the studies have a lot of subjects, well, we should get a mean difference right around here. But if the studies have fewer subjects, well, that effect size, since it's going to be less accurate, all right, is going to be more spread out. Okay, so if we have very, very few subjects, the effect size that we calculate is going to be very, very spread out. Whereas if we have a lot of subjects, the effect size is going to be honed in to what it truly is. Now, with the funnel plot, we should see dots all over the funnel. All right, something like what we find here. All right, if we see dots all over the place, well, that's kind of what we expected. All right, the best studies with the most subjects are close to the truth. The studies that have very few subjects, we see them all over the place. All right, so there's dots all in the funnel. We do not have evidence of publication bias. However, if we see a funnel that looks something like this, all right, so there's lots of dots over in this part, but there's no dots over here. What that means is that when we do the study well, when we have a lot of subjects, okay, the study can be published regardless of the result. But if we have few subjects, the study only gets published if we find a particular effect, if we say that there's a true difference between these two means. Ooh, that's odd, okay? So these, since we don't have any studies right here, these seem not to be getting published, even though these studies over here that have just as few subjects get published. So this is some evidence of publication bias right here. All right, so we have evidence of publication bias if this funnel plot is weighted one direction and not another. Okay, so we can point out the publication bias of a particular effect in the literature by examining these funnel plots. Really cool. So let me give you two famous examples of meta-analyses. This first one is by Mal in 2006, and it studies something that is in many social psychology textbooks, and heck, is even in many general psychology textbooks. This is the actor-observer bias. This is a phenomenon that you talk about in social cognition. Actor-observer bias is the bias that when you do something, you attribute whatever happens to some, one second here. Sorry. I wanted to confirm that I knew what I was talking about before I did it. My apologies. I was right though, so that's good. It's actor-observer bias is the bias that you attribute actions of yourself as due to the environment around you. All right. Why did you do well on that test? Well, it's because you studied hard. Why is it that your date didn't go well? Well, the situation, the location wasn't that good. So you attribute things, your successes and failures, to things that are external. However, for other people, if that other person does well on the test, well, it must be because they're smart. If that person, their date goes well, it's because they're a lousy person. So we make external attributions for other people, that it's the environment, or that it's, let me back up. For other people, we make internal attributions. I'm sorry, I messed that up for you. We make internal attributions. Those individuals, the reason why they are successful or they fail, it's due to themselves. They're either smart or they're bad, but it's some quality about them. However, for ourselves, all right, we make attributions that are external. So it's something that has to do with external forces that's leading us to succeed or us to fail. And this is a phenomenon that is talked about in social psychology for quite some time. All right, and it's in all the textbooks. So Mal wanted to check this out, wanted to see if the actor-observer bias was really true. So what Mal did is conducted a meta-analysis here, and we have a funnel plot here, but it's a bit of a reverse funnel plot. So the precision of the study increases as we go down the graph. And if we look at the average effect size here, we see the average effect size is 0. Ooh, this actor-observer bias that we've been talking about for decades turns out not to actually be true. And yet it's been in all the general psychology textbooks and all the social psychology textbooks. So that's no good. What Mal was able to do is look at what is the moderating variable. All right. And what we see, the major moderating variable is it depends on if we are attributing positive events or if we're attributing negative events. And this is the old self-serving bias that we've known about for quite some time. If it's a positive event, you are attributing it typically to yourself. So you did well on the test. Well, you're not going to look at something external. You're going to say it's because I am successful, because I'm smart. If you fail, you're going to attribute it to something external. Whereas when we're making attributes about other people, okay, when we make attributes about other people, we typically make just internal attributions for them when something bad happens, and we make external attributions when something positive happens to them. All right, so the bias is not as simple as the regular actor-observer bias. It really depends on if we're interpreting positive or negative events. All right, so that's something useful that came out of the meta-analysis by Mal. All right, let me talk about one more example of meta-analysis. So we have this meta-analysis by Cameron and Pierce, who are two behaviorist or behaviorist-minded researchers. So they care a lot about operant conditioning, reinforcement, punishment, and that sort of thing. And they took umbrage with some part of Ryan and Deasy's self-determination theory. So I don't know if you've had IO psychology, where you'll probably talk a decent amount about self-determination theory, but one attribute of self-determination theory talks about the difference between intrinsic motivation and extrinsic motivation. Intrinsic motivation is you enjoy doing something because it's rewarding in and of itself. So you enjoy painting pictures because painting pictures is fun to you. And we can contrast that with extrinsic motivation. Extrinsic motivation, you do the thing for some outside reason. So maybe you enjoy painting pictures because you can get money painting pictures. All right. So did you take a history class because you personally enjoyed it, or did you take it to fulfill some requirement? So the difference between extrinsic and intrinsic motivation. Now, Ryan and DC argue that if you reinforce somebody for something that they're intrinsically motivated for, that it gets rid of the intrinsic motivation. So if someone is enjoying painting pictures and you start paying them money for painting pictures, well, they're no longer going to be intrinsically motivated for painting the pictures. They're only going to rely on that extrinsic motivation. So you need to be really careful about reinforcing people for doing something that they might naturally love. So that's Ryan and DC's argument. Cameron and Pierce say, no, the data does not confirm what you guys are talking about. The data is not in alignment with your theory. And Cameron and Pierce look at many studies in which people receive either tangible rewards or verbal rewards for doing some kind of activity. Okay, maybe it's collecting cards, maybe it's painting pictures, maybe it's solving math problems, and they see whether or not this ruins the intrinsic motivation. And they find that it doesn't. Okay, we can see this both in terms of the amount of free time that people spend doing the task when they're not reinforced for it, and in their attitude for the task. So for instance, Ryan and DC might argue that if you reward somebody for doing the task, their attitude for it will decrease. Okay, they actually hate doing the task now. Okay, Cameron and Pierce argue that that's a bunch of BS. All right, and this is a huge topic of debate, and Cameron and Pierce and Ryan and DC are all at odds with one another. But very famous meta-analysis, very important. All right, so that's effect size. All right, we're talking about practical importance. How big is that mean difference truly? And the way that we typically measure it, if we're looking at two differences between means, is we're looking at Cohen's d. Now, a related concept is power. Power is the likelihood of rejecting the null hypothesis, given that the null hypothesis is false. So if there's truly a difference, what is the probability that we'll actually reject the null hypothesis? Okay, the probability that we reject the null hypothesis when we should. Now, remember, for null hypothesis significance testing, we set the type 1 error rate beforehand. We don't set the type 2 error rate. The type 2 error rate, remember, is the probability of us retaining the null when the null hypothesis is false. Okay, it's the percentage of time that we miss, because we don't know the effect size. We don't know truly the difference between the population means. Okay, if we knew that, we wouldn't have to conduct the dang study. All right, so we can't really estimate power beforehand. Okay, so another way of looking at power is it's the probability for us avoiding a type 2 error. And in fact, I probably have this in my next slide, but you know what? I like drawing. Remember, our probability of making a type 2 error we call beta, and this is our beta. So our power is 1 minus beta. So 1 minus beta, that is our power, the power of our study. Okay, so power is a function of both the effect size, all right, how large the effect size is. If the effect size is big, we're automatically going to have a lot of power because it's easy to detect the effect, and the sample size. All right, the more subjects that we have, the easier it is to tell that there is a significant difference. All right, so I can actually fill in a little bit more of this table that we've looked at beforehand. So we've got the null hypothesis here. We've got if the null hypothesis is actually true, if the null hypothesis is false, and we have whether or not we reject or retain the null hypothesis. Okay, power is when the null hypothesis is false. So there's truly a true population mean difference, and we correctly reject the null hypothesis. So 1 minus beta, this is our power. Okay. So another way of looking at power here, again, these are our population distributions. Okay, these are our population distributions, and this is we calculate the rejection region, and this little part here is the probability that we make a type 1 error. But all of this in this lighter shade of purple right here, that's the amount of power that we have. Okay, that's the power that we have to reject the null hypothesis if the null hypothesis is actually false. And again, we don't know what these population distributions actually look like when we conduct a study. Okay, we don't know what truth is, but if we know what truth is, we can look at the likelihood that we would reject the null hypothesis here. Okay, there are 5 ways that we can change power. Now, we typically want to have good power of the study. We don't want to be underpowered, that if there is an effect, we're unlikely to find it. If that's the case, why even conduct the study to begin with? Okay, we want to have good power to detect an effect. So there's 5 things that we can do to change the power of our study. Some of these things are allowed, some of these things are not allowed, but these 5 things will change the power of our study. Typically, the power that we want to have is around 0.8 or 80%. So there's an 80% chance, if there's a true population mean difference, that we reject the null hypothesis. Again, that is kind of a textbook answer, and you might want to change what your power level is. Okay, maybe you want to be more certain. Maybe you want to have a greater amount of power. But the textbook says that the amount of power that you want to have for a study is around the 0.8 range. Okay, what are 5 things that we can do to change the power of a study? Okay, the first thing that we can do is increase alpha. So this is our type 1 error rate. If I change my type 1 error rate from 5% to 10%, now I am increasing my type 1 error rate, no duh, but also notice that I'm increasing my power, all right? The type 1 error rate and type 2 error rate are at odds with one another for the most part, all right? If we are more lenient about accepting or if we're more lenient about rejecting the null hypothesis, okay, then we have a greater amount of power, but it comes at a cost. Okay, the cost is the increased probability of committing a type 1 error. So this is a no-no. No one ever does this. It would increase power, but it also increases type 1 error rate. So we don't do it. All right. So we could switch from a 2-tailed test to a 1-tailed test. Okay. Suppose we know where the population mean difference is. Okay. If we do a 2-tailed test, this is how much power we have in the light purple shade here. What we could do is, instead of doing a type 2 or a 2-tailed test, we can switch to a 1-tailed test. All right. Our type 1 error rate does not change. It's 5% here, it's 5% here, but our power has changed. All right. So switching to a 1-tailed test increases our power, but we have to know the direction of the population mean difference. All right. Because again, if the population mean difference is over on this side, if we predicted that mean 1 will be greater than mean 2, but in actuality mean 2 is greater than mean 1, we are unable to reject the null hypothesis in situation 2. So if we have a guess, an educated guess, we can do a 1-tailed test and we increase the amount of power that we have. All right, that's good. In some situations, that's good. If you are doing a study and you're completely blind as to where the effect is going to be, not super helpful, but it is going to increase power if you know the direction of the population mean difference. All right, so that was 2. Now let's talk about 3 and 4. And we see the same thing happening here. So these are sampling distributions. Okay, these are our sampling distributions here. And we could increase our number of subjects. If we increase the number of subjects, we are going to take that standard error and decrease it. Okay, remember here that standard error is the population standard deviation over the square root of n. If we increase n, the standard error is going to get smaller and smaller and smaller. Okay, what that's going to do is it's going to lead the variance, the standard deviation of these sampling distributions, to get smaller and smaller and smaller for the distributions to get more and more compact. All right, notice how the amount of power changes from A to B. So if we increase the number of subjects, we are always going to have more power. And typically this is the solution to power. If we have to do one thing, easy thing to do, increase the number of subjects. You're more likely to find a significant result. Okay, but that's not all that we can do. So if we want to decrease the standard error, one thing that we could do is we could take n and we could increase that, or we could take the population standard deviation and decrease that. That would have the exact same effect here. So how would we do this? All right, there's many things that cause scores to vary. If your experiment is not well controlled, okay, if your experiment, some of the subjects get the condition this way, some of them get the condition that way, there's multiple things that might impact their score. Well, there's going to be more variance. There's going to be more variance in people's scores. So the more well controlled your experiment is, the smaller that population standard deviation is going to be. So if you do a good job of controlling your experiment, that population standard deviation is going to decrease and your amount of power is going to increase. Another thing is that you could get more homogeneous subjects. All right, so if I were looking at a study of cognitive abilities and I used subjects from the ages of 10 to the ages of 90, that increases my generalizability of the study definitely, but those scores are going to be all over the place. Okay, that's going to lead to an increased population standard deviation. That's going to lead me to have less power. If I just use college subjects that are all from the same university, that are all the same age, that all have similar cognitive abilities, I'm going to have less of a variance in my scores. And this is going to lead me to an increased amount of power. I sacrifice generalizability, but I increase my ability to detect an effect. All right, maybe we are comfortable with that. Maybe we're comfortable about that, especially if college students are the only subjects that we have. But again, it's going to increase our power because they're very homogeneous. The population standard deviation is going to be very small. Okay, so increasing your sample size, always a good thing to do to increase power. Try to control your experiments very well. That's going to decrease the population standard deviation. Getting more homogeneous subjects, that sacrifices generalizability, so we want to be a little bit cautious about that. And the last thing that we can do here is we can increase our experimental manipulation. All right, and this will increase the difference between means. This will increase the amount of power that we have. All right, if we believe a nap increases someone's memory, maybe instead of doing a 10-minute nap, you do a 30-minute nap. With a 10-minute nap, there's probably a small difference. With a 30-minute nap, there's probably a great difference. If we are training somebody, instead of doing 3 days of training, we do 6 days of training. There's going to be probably a greater effect. Okay, if we think that cocaine increases someone's attention, instead of giving them 3 units of cocaine, you give them 100 units of cocaine. Don't do that. That's probably a bad idea. But it would increase the population mean difference. All right. And if the population mean differences are already greater, we are better able at determining if there is a true effect. We have more power. Okay, so these 5 things change the amount of power that we have in our study. All right, so there are 2 kinds of power analyses. All right, there's two kinds of power analyses that we can do. In fact, SPSS just recently, like within the past 6 months, has come out with a way of doing power analyses. It used to be the case that we had to use another program called G-Power. And in fact, when you take research methods, you might learn how to do G-Power. I would love to teach you, but man, there's so much that I've got to cover in this class that I just kind of leave that up to some research methods professors. But we will learn how to do it using SPSS. So two kinds of power analyses. One is a post hoc power analysis. Post hoc, how good is you guys' Latin? Post means after, like post-game analysis. That's after the game. Hoc, this means this, all right? So after this being the experiment. So post hoc is a power analysis that we conduct when the experiment is already over. All right, we do a post hoc power analysis if we truly don't find an effect. Okay, we retain the null hypothesis, and we do the post hoc power analysis to determine if we had a decent amount of power to detect the effect. So we look at the effect size as calculated by our study, and then we ask the question, did we have enough power to detect that effect? All right. So we see post hoc power analyses very frequently in some studies. My personal opinion is that they're very useless because, one, you don't know what the true population mean difference is. You don't know what the true effect size is. And obviously, you didn't have very much power because you didn't reject the null hypothesis. So post hoc power analyses are dumb, okay? I might show you how to do one, but don't ever do one in your paper. They're really, really dumb. A better way of doing power analyses is an a priori power analysis. All right, what's a priori mean? A means like from, and priori means beforehand, like something that's prior is something that's beforehand. So a priori power analysis is a power analysis that we do before the study begins. This is a good way of doing a power analysis. If you're planning a study, how many subjects should you run? I've already mentioned researcher degrees of freedom. You shouldn't just run subjects until you find the effect. What you should be doing is looking at the literature, trying to see what effect size you think you're going to find, and then you look at how many subjects you need to have adequate power to determine that effect before you begin your study. This is something very important to do. All right, a priori power analyses are a very good thing to do. How many subjects should you run? And so that's a very powerful tool that you can use. If you can estimate the effect size, or heck, you might say, hey, a large size effect according to Cohen is a Cohen's d of 0.8. What's my probability of finding a large size effect? And you calculate that and you report that. So you can use that, one, to determine how many subjects that you actually need. I've actually used this in my very first publication. I found, I was actually predicting that I would find no difference between these two conditions. But you can never accept the null hypothesis. So what we ended up doing, myself and Gil Einstein, my undergraduate advisor, is we said, well, if this was even a small-sized effect, okay, we had adequate power to find a small-sized effect, and yet we didn't. So that's the argument that we made using kind of a priori power analyses by looking like, if the effect was this and we have these many subjects, what is the, how much power do we have? Okay, that's not actually a priori, that's a post hoc power analysis, but in that way it's good, okay, because the effect size that we used was an effect size that was already specified by Jacob Cohen. So in that case, the post hoc power analysis was not dumb, but most of the time they are, because you're using the effect size that you actually found in the study, and that's kind of dumb. All right, so that was probably a decent amount of information. Let's stop there and get ready for t-test. We'll talk about that soon. Thank you guys and have a great day. Bye-bye.